Now, one question that we've always asked before, right, but we haven't gotten around to yet, except, very, very briefly, is, so what can we represent with a multi-layer perceptron, right? Can we, for example, can we represent any Boolean function? Remember, we already saw the answer to this one today, but then there were all those beeps and they erased your memory. Right? We can represent any Boolean function with a neural net with a multi-layer perceptron. How? Right? Let's say the function is in the NF. One unit for the OR, right, and one unit for each of the ands. Okay, very good. But what about continuous functions, right? This is the other interesting thing about neural networks is that, just like your brain, they don't really care about digital versus analog. They can do, both things. Can we represent any function, continuous function, right? So now thinking of doing regression using neural network, can I represent any function using a multi-layer perceptron? Well, this is not an obvious question, and somebody figured it out and then proved theorems about it. And here's the rule: if your function is bounded, meaning it never goes to plus or minus infinity, in fact, a network with one hidden unit, with one hidden layer, is enough. But you might need an infinite number of hidden units. So that's the good news and the bad news. What is the intuition for this? The intuition for this is actually quite simple, right? Let's say you have an arbitrary function, right? You need to approximate this using a bunch of sigmoids, right? So how do you do that? Well, let me do this in color. What you do is you put one sigmoid here, right? And then you put a sigmoid with a negative, slope right here, right? And then another one here, right? And then you need to put a positive one here, right? So every time the function goes up, you put a sigmoid to make it go up, and every time it goes on, you put an inverted sigmoid to make it go down, right? So clearly, I can approximate anything this way. Also, clearly, if I want to approximate it exactly in the worst case, I need an infinite number of sigmoids, right? Because for every, unless the shape of that changes exactly sigmoid, which it generally won't be, I will need a lot of sigmoids to reproduce the function exactly. Okay? Nevertheless, what this means is that neural networks with sigmoids are a pretty good approximation for general functions. This is also true if you use radial basis functions as your approximant, right? With other functions, well, it depends on the function. Okay. Now, what happens if my function? If my function can actually go to infinity, right? Because a lot of functions go to infinity. At that point, actually, you can't do this with just two layers. Again, the reason for this is not obvious, but clearly that case is going to be harder, right? How do I make a jump that's both infinite in size and of the right shape, right? At that point, I actually need two hidden layers. But that's not bad, right? So, with a multi-layer perceptron with two hidden layers, I can approximate any continuous function. In the worst case, with a very, very large number of units. But, that's better than nothing. Okay? So this is good. This means that, neural networks are actually pretty general. And I can see the kind of argument that people used to have in machine learning circa 1990. It was like, the instance-based learning people said, like, I have a theorem that says I can do anything with nearest neighbor, so why bother with the rest? And the decision tree people said, I have a theorem that shows you can do everything with the decision tree. And the neural network people said, like, I have a theorem that shows you can do everything with the neural network, so forget about the rest. The answer to this, of course, is that, sure, you have all these theorems, but they're not enough. It's not enough to be able to represent something. You need to ask whether this is a better way to represent it in terms of being a more compact model, and very importantly, whether it's easier to learn this function with your representation than with the other one. And once you ask that question, which is actually the important one, in the real world, are you going to learn this or not, versus in principle, then none of these dominates. Sometimes the decision tree wins, sometimes the neural network wins. So, all those, ideological wars of the 90s, have, largely faded away, and good machine learning people today know to have many things in their toolkit. Back then, you have one hammer, whether it was backprop or decision trees, and you tried to hammer everything with it. This is not the right approach, right? And in fact, when we talk about theory next week, we will see some deep reasons why this actually has to be the case. Any questions about this? So multi-layer perceptrons are expressive, but that's not the end of the story. Okay, so final issue, overfitting. As always, if your model is powerful enough, you need to worry about overfitting. And certainly, we just saw that the model is powerful enough. If you keep adding hidden units, you'll be able to model anything, even be able to just memorize the input. Okay. So by the way, one of the things that people spend a lot of cycles on is figuring out how many hidden units to have, because that really is a crucial parameter. Okay. So here's another nice little example of learning curves. This now is with error instead of accuracy. And now this is my number of weight updates. Okay? And this is from a robot perception task. And again, we see the usual phenomenon here of the training set keeps getting lower. Sorry, the training error keeps getting lower. But the error on the validation set, at first it goes down, but then it starts to slowly inch up, right? And what we would like to do, of course, is to stop somewhere around here. Okay? By the way, just so you don't get the impression that learning curves are always like this, here's another couple of learning curves from the same task. But this always happens. This also happens. Here's my error on the training set, right? It looks beautiful. It goes to 0 very quickly. The error on the validation set actually does something a little more unusual, which is, yeah, at first this looks like the normal thing, right? It goes down to a minimum, and then it starts to go up again. But then, after a while, it actually starts to go down again. In fact, you can prove, it's unfortunate, but you can, that in principle, anything can happen in a learning curve. Right? You have this very complicated landscape. Sometimes you slow down and then you speed up again. Sometimes you get stuck and then you come unstuck. You kind of inch your way across that plateau and then you find another, exit in this highly multidimensional space. So notice that in this case, I actually did not overfit. The best network was this one. Okay? Nevertheless, you should still not trust that network, because notice there's still this very big difference between the error that you think you got and the error that you're really getting. Okay? Nevertheless, in general, you need to have overfitting control mechanisms, which, if this is the case, will let you go all the way to here. Otherwise, will make you, stop early. Okay? So, the question for us is, how do we combat overfitting in neural networks? And, here's 4 different ways, all of which have their pros and cons. One way. Somebody had a question?
How it can learn something like sine curve, where the input keeps on increasing?
One more time, sorry?
Like, how can neural network learn a sine function, say, for example?
Oh, sure. That's a good example. Let me show you. Well, actually, I don't even have to show you. I'm just going to pretend that this curve was a sine. You see?
But the input keeps increasing and it has to extrapolate.
No, so remember, what I'm trying to do is this is my x, right? And I'm trying to learn to produce this y as a function of my x, right? So what happens is that I have a sigmoid for this part of the sine that goes up, and then another sigmoid of the same magnitude that basically takes you down again, and then another sigmoid that makes you go up again, right? So I can approximate. So now, truth in advertising, what I'm going to get is not exactly a sine wave. It's going to look, not quite the right shape, but it's going to be a fairly good approximation. Okay. And now, if you want to make the approximation better, now you need to put some thinner sigmoids there to just make it be closer. But you can certainly learn it. Okay. All right.